Welcome! In this session, we'll dive into the problem titled Partition Array into Disjoint Intervals. Together, we'll understand the problem statement, explore various approaches, and discuss their complexities. Let's get started. In this problem, you are given an integer array called nums, and your task is to partition the array into two contiguous subarrays, left and right. These two parts must satisfy three specific conditions. First, every element in the left subarray must be less than or equal to every element in the right subarray. Second, both left and right must be non-empty and together form the entire array. Lastly, the total length of left and right must exactly match the length of nums. Your goal is to return the length of the left subarray after finding such a valid partition. If there are multiple valid partitions, you should return the one that results in the smallest possible length of left. The input consists of an integer array with constraints on its size and values, and the output is an integer representing the required length of left. Let's look at an example to clarify this. Here, the input array is 5, 0, 3, 8, 6. A valid partition can be made by splitting the array into left equals 5, 0, 3, and right equals 8, 6. Notice that the maximum value in left is 3, and the minimum value in right is 8. Since all elements in left are less than or equal to all elements in right, the partition satisfies the conditions. The length of the left subarray is 3, which is the output for this example. Now, consider another example with the input array 1, 1, 1, 0, 6, 12. Here, the valid partition is left equals 1, 1, 1, 0, and right equals 6, 12. The maximum value in left is 1, and the minimum value in right is 6. Again, all elements in left are less than or equal to all elements in right, so this partition is valid. The length of left in this case is 4, which is the final output. This example demonstrates that the partition may include multiple elements from the beginning of the array to ensure that all conditions are met. In another scenario, let's say the input array is 1, 2, 3, 4, 5. Here, the smallest valid partition is left equals 1, and right equals 2, 3, 4, 5. The maximum value in left is 1, and the minimum value in right is 2. Since 1 is less than or equal to 2, this partition satisfies the conditions. The length of the left subarray is just 1, which is the output. This example shows that if the array is already sorted in ascending order, the smallest valid left partition will only include the first element. When analyzing edge cases, several interesting scenarios come up. If all elements in the array are the same, such as 3, 3, 3, 3, the output will return the smallest valid partition, which includes only the first element in left. For arrays already sorted in ascending order, like 1, 2, 3, 4, 5, the left partition will again contain just the initial element. On the other hand, for arrays sorted in descending order, such as 5, 4, 3, 2, 1, almost the entire array needs to be included in left to satisfy the conditions, leaving only the last element in right. These cases highlight the importance of carefully considering the array's structure when determining the partition. To begin, let's consider the brute force approach. The idea here is to test every possible way to split the array into two parts, a left subarray and a right subarray. For each split, we check whether all elements in the left subarray are less than or equal to all elements in the right subarray. If this condition is met, we identify the partition index. The process involves iterating through all possible partition points, computing the maximum value of the left subarray and the minimum value of the right subarray for each split, and then checking if the condition holds. While simple to implement, this method is computationally expensive, as we repeatedly calculate the maximum and minimum values for overlapping subarrays, leading to a time complexity of O(n superscript 2). This inefficiency makes it unsuitable for handling large arrays, despite its intuitive nature. Now, to improve on the brute force approach, we can use the optimized two-pass solution. The key insight here is to pre-compute the maximum and minimum values for all subarrays, eliminating redundant calculations. Specifically, we define two auxiliary arrays, max_left, which stores the maximum value for every prefix of the array, and min_right, which stores the minimum value for every suffix. The maximum values for the left subarrays are calculated in a left-to-right pass, while the minimum values for the right subarrays are calculated in a right-to-left pass. Once these arrays are populated, we can efficiently find the partition index by simply iterating through the array and checking where the maximum value of the left subarray is less than or equal to the minimum value of the right subarray. This approach drastically reduces the time complexity to O(n) by avoiding redundant work, though it does involve additional space for the auxiliary arrays. The two-pass solution is a significant improvement in terms of time complexity, but it still requires extra space for the auxiliary arrays. To optimize further, we can adopt a space-efficient single-pass solution. Instead of pre-computing and storing values in separate arrays, we dynamically track the necessary maximum and minimum values as we traverse the array. This eliminates the need for additional storage. The key idea is to maintain two variables, max_so_far, which keeps track of the maximum value encountered so far, and left_max, which represents the maximum value in the left partition. Additionally, we dynamically adjust the partition index during the traversal. This approach achieves the same time complexity of O(n), while reducing the space complexity to O(1), making it more efficient overall. To implement the single-pass solution, we initialize three variables, max_so_far set to the first element of the array, left_max also set to the first element, and the partition index set to 0. As we iterate through the array, we continuously update max_so_far to keep track of the largest value we've seen so far. When we encounter an element that is smaller than left_max, it indicates that this element cannot be part of the right partition yet, so we update the partition index to the current position and adjust left_max to the current value of max_so_far. At the end of the traversal, the partition index, offset by 1, gives us the smallest index where the array can be split. This method is optimal in both time and space, but it does require careful handling of the dynamic updates to ensure correctness. The chosen strategy for this problem is the optimized single-pass solution. This approach stands out because it achieves the best possible efficiency in both time and space, with a time complexity of O(n) and a space complexity of O(1). By avoiding the use of auxiliary arrays, this method is particularly well suited for memory-constrained environments. The critical insight that enables this solution is the realization that we can dynamically track the partition index using left_max and max_so_far. While the logic is slightly more complex compared to the two-pass solution, it is manageable and scales effectively for larger arrays. We weighed the trade-offs of the brute force, two-pass, and single-pass solutions, and the single-pass approach emerged as the most balanced and efficient option. By focusing on dynamic updates instead of pre-computations, it offers a robust and elegant solution to the problem. To tackle the problem of partitioning the array into disjoint intervals, let's start by clearly defining the task. We are given an array of integers, and our goal is to split it into two subarrays, left and right, at an index I. The key requirement is that all elements in the left subarray must be less than or equal to all elements in the right subarray. Furthermore, we need to find the smallest such index I that satisfies this condition. A simple strategy to start with is a brute force approach. Here, we can try every possible partition index I and check whether the condition holds. Specifically, for each partition, we verify if the maximum value in the left subarray is less than or equal to the minimum value in the right subarray. If this is true for a given I, we return it as the answer. While this method is intuitive, it involves significant computation, as we need to calculate the maximum and minimum values for each potential partition, which can be quite slow for large arrays. In the brute force approach, we iterate through all possible partition indices, starting from 0 up to n2 where n is the size of the array. For each index I, we calculate the maximum value in the left subarray, which includes elements from the start of the array up to I. Similarly, we calculate the minimum value in the right subarray, which includes elements from I+1 to the end of the array. Once we have these values, we check whether the maximum value in the left subarray is less than or equal to the minimum value in the right subarray. If this condition is met, we return the current index I. However, this approach is computationally expensive because each calculation of the maximum or minimum value takes O(n) time, and we repeat these calculations for each partition index. This results in an overall time complexity of O(n squared, which is inefficient for larger input sizes. To overcome this, we need an optimized approach that avoids redundant calculations. We can significantly improve the efficiency of our solution by using an optimized approach that pre-processes the array. The key idea is to use auxiliary arrays to store pre-computed values, which will allow us to quickly check the partition condition without recalculating maximum and minimum values repeatedly. Specifically, we create two additional arrays, left_max and right_min. The left_max array stores the maximum value from the start of the array up to each index, while the right_min array stores the minimum value from each index to the end of the array. To pre-compute left_max, we initialize the first element as the first element of the input array. Then, for each subsequent index, we calculate the maximum of the previous value in left_max and the current element of the input array. Similarly, to pre-compute right_min, we initialize the last element as the last element of the input array. Then, we move backward through the array, calculating the minimum of the next value in right_min and the current element. Once these arrays are ready, we can efficiently find the partition index by iterating through the array and checking where the value in left_max is less than or equal to the corresponding value in right_min. The use of pre-computation is crucial to improving the efficiency of our solution. By storing the maximum values for the left subarray and the minimum values for the right subarray in auxiliary arrays, we eliminate the need to repeatedly compute these values during each iteration. This reduces the time complexity of finding the partition index from O(n)² to O(n). The condition left_max, I, equals right_min, I plus 1, guarantees that all elements in the left subarray are less than or equal to all elements in the right subarray, fulfilling the requirements of the problem. It's also important to consider edge cases, such as when the array has only two elements, when all elements are identical, or when the array contains both negative and positive numbers. These scenarios highlight the robustness of the optimized approach and ensure that it handles all possible inputs correctly. To implement the optimized approach, we rely on specific data structures. The input array ARR is used as the foundation of our computation. Additionally, we utilize two auxiliary arrays, left_max to store the maximum values up to each index and right_min to store the minimum values from each index to the end. The space complexity of the solution is O(n) due to these two auxiliary arrays. As for the time complexity, pre-computing left_max and right_min each requires a single pass through the array, resulting in O(n) time. After pre-processing, finding the partition index involves another single pass through the array, making the overall time complexity O(n). This combination of O(n), time complexity and O(n), space complexity makes the solution highly efficient, even for large input sizes. Let's consider an example to see the optimized approach in action. Suppose the input array is ARR equals 5, 0, 3, 8, 6. First, we compute the left_max array as 5, 5, 5, 8, 8, which represents the maximum values from the start of the array up to each index. Next, we compute the right_min array as 0, 0, 3, 6, 6, which represents the minimum values from each index to the end of the array. Now, we iterate through the array to find the partition index. At index 2, we check the condition left_max, 2 equals right_min, 3, which translates to 5 equals 6. Since this condition holds true, we determine that the partition index is 2. This means the left subarray is 5, 0, 3, and the right subarray is 8, 6. The output of the function is therefore 2. The solution employs a two-pass approach to efficiently find the partition index for the array. First, we initialize two auxiliary arrays, max_left and min_right, to keep track of the maximum values from the beginning of the array to the current position and the minimum values from the end of the array to the current position, respectively. These arrays help us identify a valid partition index in O(n) time. We start by populating max_left. The first element is initialized to nums, 0, as it represents the maximum value from the start up to index 0. For each subsequent index I, the value at max_left, I, is updated as the maximum of max_left, I1, the maximum up to the previous index, and nums, I, the current element. This ensures that max_left contains the maximum values for all positions from the left. Next, we construct min_right. The last element is initialized to nums, -1, as it represents the minimum value from the end up to the last index. We then iterate backward through the array, updating min_right, I, as the minimum of min_right, I plus 1, the minimum from the next index onward, and nums, I, the current element. This ensures min_right contains the minimum values for all positions from the right. Finally, we iterate through the array starting from index 1 to n1. For each index I, we check whether max_left, I1, the maximum value in the left subarray, is less than or equal to min_right, I, the minimum value in the right subarray. If this condition is satisfied, I is the partition index, and we return it. The algorithm is efficient with a time complexity of O(n), due to the 2 passes required to populate max_left and min_right, and a space complexity of O(n) for the auxiliary arrays. It also handles edge cases, such as arrays with all identical elements or strictly increasing/decreasing arrays, ensuring correctness under all valid inputs. Here, we start by importing necessary utilities and defining our solution class with the method partition disjoint. The input is an integer array nums, and our goal is to find the smallest index at which the array can be split into 2 disjoint subarrays. To achieve this, we use 2 auxiliary arrays, max_left and min_right. The max_left array keeps track of the maximum value encountered from the left up to each index, while min_right keeps track of the minimum value encountered from the right. First, we initialize max_left with the value at index 0. Then, using a loop, we iterate through the array starting from index 1, updating max_left so that each position contains the maximum value from the start of the array up to that index. Similarly, the min_right array is initialized with the value at the last index and is built in reverse order. Using another loop, we iterate backward through the array, ensuring that each position in min_right represents the minimum value from that index to the end of the array. Finally, we look for the partition index by iterating through the array, checking where the maximum value in max_left for the left side is less than or equal to the minimum value in min_right for the right side. The first such index is our partition point. If we find a valid partition index during the loop, we return it immediately. However, if the loop completes without finding such an index, we return -1 as a fallback, though this case should not occur if the input constraints are adhered to. The method ensures that we efficiently calculate the partition index by leveraging the properties of the max_left and min_right arrays, which allow us to make the comparison in a single pass after pre-processing. This approach runs in O(n) time, as it involves 3 linear scans of the array, making it optimal for this problem. In this problem, we are given an array nums, and we need to partition it into 2 disjoint intervals, a left partition and a right partition. The key requirements are that every element in the left partition must be less than or equal to every element in the right partition, and the left partition must be as small as possible. The goal is to return the size of the left partition. To solve this, we first construct an auxiliary array called max_left, which helps us track the maximum values from the start of the array up to each position. For example, if nums is 5, 0, 3, 8, 6, we initialize max_left, 0, to the first element, which is 5. Then, as we move through the array, we compute the maximum value seen so far at each step. This gives us max_left equals 5, 5, 5, 8, 8. The values in max_left represent the largest element from the start of the array up to each index, which will be important for deciding where to partition the array later on. Now, we build another auxiliary array called min_right. This array tracks the minimum values from the end of the array back to each position. For the same example nums equals 5, 0, 3, 8, 6, we initialize min_right, -1, to the last element, which is 6. Then, moving backward through the array, we compute the smallest value seen so far at each step. This gives us min_right equals 0, 0, 3, 6, 6. With both max_left and min_right constructed, we can now determine the partition point. The partition point is the smallest index I where all elements in max_left up to I1 are less than or equal to all elements in min_right starting at I. In this example, we compare values and find that for I equals 3, max_left, 2 equals 5 is less than or equal to min_right, 3 equals 6. This means the left partition is 5, 0, 3, and the right partition is 8, 6. The size of the left partition is 3, so the output is 3. Let's explore another example, where nums equals 1, 1, 1, 0, 6, 12. First, we build max_left, which stores the maximum values from the beginning of the array up to each position. In this case, max_left equals 1, 1, 1, 1, 6, 12. Next, we construct min_right, which stores the minimum values from the end of the array back to each position. Here, min_right equals 0, 0, 0, 0, 6, 12. Now, we look for the partition point. For I equals 4, the condition holds because max_left, 3, equals 1 is less than or equal to min_right, 4, equals 6. This makes the left partition 1, 1, 1, 0, and the right partition 6, 12. The size of the left partition is 4, so the output is 4. For the final example, let's consider nums equals 1, 2, 3, 4, 5. First, we construct max_left, which in this case is simply 1, 2, 3, 4, 5, since each element is greater than or equal to the previous one. Similarly, min_right is 1, 2, 3, 4, 5, because each element is less than or equal to the next one. To find the partition point, we check where the condition holds. For I equals 1, max_left, 0, equals 1 is less than or equal to min_right, 1 equals 2, so this is a valid partition. The left partition is 1, and the right partition is 2, 3, 4, 5. The size of the left partition is 1, so the output is 1. In analyzing the time complexity of the algorithm, we observe that it consists of three main steps. First, we build the max_left array by iterating through the input array nums from left to right. At each index, we compute the maximum value encountered so far, which takes constant time per iteration. Since the loop runs 4 and 1 iterations, the time complexity for this step is O(n). Next, we build the min_right array by iterating through nums from right to left. Similarly, we compute the minimum value seen so far at each index, which also involves constant time per iteration. This step also runs 4 and 1 iterations, giving it a time complexity of O(n). The final step involves finding the partition index by iterating through the input array from index 1 to n1. During this loop, we compare the values of max_left and min_right at each index to determine the partition point. Since each iteration involves a constant time comparison and the loop runs 4 and 1 iterations, the time complexity for this step is O(n). When we combine the contributions of these three steps O(n) for building max_left, O(n) for building min_right, and O(n) for finding the partition index, the total time complexity of the algorithm becomes O(n). On the space complexity side, the algorithm uses two auxiliary arrays, max_left and min_right, each of size n. This means that both arrays contribute O(n) to the space usage. In addition to the two arrays, the algorithm uses a small amount of memory for scalar variables such as n and loop iterators. These variables require constant space, or O(1). When we combine the contributions of the max_left array, the min_right array, and the scalar variables, the total space complexity is O(n) plus O(1), which simplifies to O(n). To put this into perspective, consider a naive brute force approach. In such an approach, we would iterate over all possible partition indices and compute the maximum in the left partition and the minimum in the right partition for each index. This would require O(n) operations for each of the n1 possible partitions, resulting in an overall time complexity of O(n squared). By contrast, the optimized approach precomputes the maximum and minimum values in linear time, reducing the overall time complexity to O(n). When considering the best, average, and worst cases for this algorithm, the time complexity remains O(n) in all scenarios. In the best case, the partition index might be found early during the final loop, but the pre-computation steps for max_left and min_right still require linear time. In the average case, the algorithm processes the entire input array to build these auxiliary arrays and locate the partition index, maintaining a time complexity of O(n). Even in the worst case, where the partition index is located at the end of the array, the dominant operations are still the linear passes over the array. Mathematically, the time complexity is derived from the three linear passes, each contributing O(n), resulting in O(3n), which simplifies to O(n). Space complexity is dominated by the two auxiliary arrays, each requiring O(n) space and constant space for scalar variables, leading to a total space complexity of O(n). This demonstrates that the algorithm is highly efficient in both time and space usage, making it well suited for large input sizes. One common mistake when solving this problem is misunderstanding the partition definition. Remember, all elements in the left partition must be less than or equal to all elements in the right partition. It's not just about comparing adjacent elements, it's about ensuring this rule holds true across the entire division. Violating this rule leads to invalid partitions that don't meet the problem's requirements. Another frequent error is off-by-one mistakes when iterating through partition points, such as forgetting array boundaries or allowing empty subarrays. This can cause runtime errors or produce solutions where the array isn't fully covered. Additionally, some candidates try to sort the entire array to determine the partition, which unnecessarily increases the runtime complexity from O(n) to O(n log n). This problem can often be solved more efficiently without sorting. Lastly, ignoring edge cases, like arrays with duplicates or arrays where all elements are equal, can result in incorrect outputs or crashes. It's crucial to consider these scenarios during both coding and testing phases. Another mistake is making incorrect assumptions about the input size. For instance, assuming the array will always be large or uniformly distributed can lead to inefficient solutions that fail for small or uniquely patterned inputs. On the brighter side, there are several insights that can help you ace this problem. A key approach is to maintain two critical values during traversal: the maximum value in the left partition and the minimum value in the right partition. This eliminates the need for repetitive comparisons and simplifies the logic. Additionally, recognizing patterns like sliding window techniques or prefix/suffix computations will make it easier to address this and similar problems. The optimal solutions usually involve either a single pass or two passes, achieving O(n) time complexity by utilizing auxiliary arrays or variables. However, if you choose to use an auxiliary array, be prepared to discuss the trade-offs, such as increased space complexity. For example, an auxiliary array like right_min requires O(n) space, while in-place tracking reduces it to O(1). Being able to explain these trade-offs during an interview can make a strong impression. This problem is closely related to others on LeetCode, such as Problem 581, which involves finding the shortest unsorted subarray, Problem 42, which focuses on trapping rainwater, and Problem 53, the classic maximum subarray problem. These problems often share underlying techniques, such as prefix/suffix computations or sliding windows. As for alternative approaches, one common method is the two-pass solution. In this approach, you calculate the minimum values from the right in one pass and keep track of the maximum values from the left in another. At each index, you compare these values to determine the partition point. While this approach is efficient in terms of time, taking O(n), it requires O(n) space for the auxiliary right_min array. Alternatively, the single-pass solution reduces space complexity to O(1) by dynamically adjusting the partition point as you traverse the array, using variables to track the left maximum and the overall minimum. However, this approach demands careful handling of the variables to ensure correctness. Lastly, there's the brute force approach, which involves checking all possible partitions by iterating over the array and validating the constraints at each division. While straightforward, this method is highly inefficient with O(n)² time complexity, making it impractical for larger inputs but useful for understanding the problem in simpler cases. Great job! We've wrapped up the problem partition array into disjoint intervals. Remember to practice the concepts we discussed and explore similar problems to deepen your understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!